Alright guys, let's go. Our assessments in 2 days. What are the updates on the robot?
Task 1 is not working.
Huh? What do you mean?
The STM isn't responding to the commands given by the RPi. This is new grounds for us. You can see the frustration, desperation. Our robot is in shambles. You can see it.
You are playing a dangerous game. If the robot stops moving, we are in deep trouble and I'm gonna come after you.
Wait, are we playing to the cameras here or are we better doing this off camera?
No! I don't care!
Well, the problem could be anywhere. It could be the algo, the RPi, or the STM.
Everyone did something to limit that problem. Congratulations.
Then you check your STM lah.
Then you check your algo code lah!
Walao!
Okay, restart.
The robot is designed to navigate and perform precise movements based on commands received from the Raspberry Pi. The robot is able to move forward and backwards to a specified distance and is able to execute precise 90-degree turns.
So by constantly taking gyroscope readings, an error is calculated and put into a PID function, which then helps our robot move straight or make accurate turns.
We also made use of the ultra sensor and infrared sensors for our second task. The robot will move straight up to a certain distance from the obstacle before performing a set of turning functions. For the second obstacle, the IR sensors are used to inch the robot forward till it no longer senses the object and will follow up with a turn.
For our pathfinding algorithm, we implemented a weighted A-star search to help the robot calculate and follow the shortest path while avoiding obstacles. This algorithm considers both distance and direction, with different weights assigned to straight moves and varying degrees of turns, small, medium, and large. It integrates a diagonal distance heuristic and accounts for the robot's direction to prioritize efficient movement. The algorithm is designed to work with a custom grid and adjust dynamically based on the robot's current position and the grid's layout.
For our simulator, we developed the interface using Pygame where the robot is programmed to turn left, right, forward, and backward. The robot navigates around obstacles by utilizing the shortest Hamiltonian path algorithm, ensuring it finds the most efficient route. JFKF commands, they allow us to have slight right and slight left turns, which are smaller turns than the usual bigger 90-degree turns. This provides more variety in the kinds of turns the robot can perform.
The RPi acts as a control center for the robot, connecting our Android application, the STM, our algorithm server, and our image recognition server together. The use of multi-threading allows for asynchronous communication and processing. The overall program flow is quite straightforward. Once all connections have been established, the Android sends the positions of obstacles to the RPi, which then forwards it to our algorithm server. The algorithm constructs a path and sends a movement command queue back to the RPi. This queue includes both movement and image capture commands. The RPi processes this queue and sends the movement commands to the STM and the image commands to the image recognition server. Semaphores and locks are placed on the message queue to ensure that commands are queued and executed in the correct order.
For the image recognition task, we employed the YOLO V8 architecture, which is known for its speed and accuracy in object detection. Our objective was to design a system capable of recognizing black-colored characters and letters on cards, regardless of the varying backgrounds. Initially, our dataset consisted of cards with black characters on plain white backgrounds. To ensure the model could perform effectively in a dynamic environment, we expanded our dataset by digitally augmenting over 8,000 images. This augmentation process involved randomizing the backgrounds with a variety of colors and patterns, making the dataset more diverse. This approach allowed us to train the model to be background agnostic, ensuring the recognition accuracy of black characters remained consistent, regardless of the complexity or color of the surrounding environment. By training on this augmented dataset, the YOLO V8 model was able to accurately identify and distinguish the black characters on the cards, even in environments where lighting and background distractions could have interfered with recognition.
Android application that enables communication between the user and the robot. It allows us to control the movement and retrieve the images recognized from the image recognition. Our UI design is Ferrari themed in particular. We envision our robot to be the fastest on the track. The homepage allows users to navigate to the three main functions of our app, which is the Arena, the Bluetooth, as well as the messaging app.
The Bluetooth page allows users to scan for nearby devices and connect to their desired device. In the paired devices list, we are easily able to select from devices we previously connected to. At the message interface, we can send customized messages to the RPi and view the message logs between the user and the RPi. On the Arena page, we can see a 20 by 20 layout grid of the image recognition maze. We can update the obstacles on the grid by tapping on the set button. Then drag the obstacles to the respective coordinates and click Done to fix the obstacles. Obstacles can only be moved when the set button is pressed to prevent accidental movement. The direction where the obstacles are facing can be set by tapping on it. When the send button is pressed, the coordinates and directions of the obstacles are sent to the RPi. Then the T1 button is pressed to start the image recognition task. The movement on the grid will simulate the real-time movement of the physical robot. Upon receiving image ID of a recognized image, the app will update the current image on the tablet along with its ID.
Then for task 2, it's simply just clicking the T2 button And
Is that it?
Yes.
Okay,
Yes.
okay, done now.
Take photo in the video, please.
Okay. I take picture. Okay, done.
Okay. Oh.
Okay, done.
Yeah, done lah.
Yeah, done lah. Can leave ah.
Okay, done.
Okay, so should we still get